There is a classroom, somewhere, in almost every country on Earth, where a teacher draws a straight yellow line across a chalkboard, places an arrow at its end, and tells a room of children that this is light. It moves in straight lines, they are told. It travels at a fixed and famous speed, 300,000 kilometers every second, the fastest anything can ever go. It bounces off mirrors at tidy angles and bends politely when it enters water. And with those few rules, the lesson is considered complete. For most people, the drawing is the entirety of what they will ever know about the thing that lets them see. And it is not so much wrong as it is a sketch of a sketch, a convenience mistaken for an explanation. The closer physicists have looked at that simple yellow arrow over the last 2 centuries, the stranger and less straight it has become, until the honest answer to the question of how light travels is no longer a line on a board, but something far harder to draw, and far more interesting to follow. Begin with the number itself, the one figure nearly everyone retains. The speed of light in a vacuum is roughly 299,792 kilometers per second, a value so central to physics that it is no longer measured but defined, fixed by international agreement, so that the meter is now derived from it rather than the other way around. That decision, made in 1983, quietly inverted the relationship between distance and light. We no longer ask how fast light crosses a known length. We declare how fast light goes and let it tell us what a length is. But the figure conceals an assumption that almost no one examines, which is that this is the speed at which light arrives anywhere it is going. It is not. It is the speed of light through perfect emptiness, through a vacuum that does not truly exist anywhere you have ever stood. The moment light enters air, glass, water, or the lens of your own eye, it slows. And the way it slows is the first place the simple story begins to come apart. Send a beam of light into a block of glass, and it will advance through that glass at perhaps 2/3 of its vacuum speed. The explanation offered to most students is that light simply moves more slowly in denser materials, as though it were a swimmer pushing through thicker water. This picture is comforting and not quite right. Light is an electromagnetic wave, an oscillating field, and as it passes through glass, its field pushes and pulls on the electrons bound within each atom, setting them vibrating in time with the wave. A vibrating charge radiates an electromagnetic wave of its own, and so each atom sends out a faint secondary wave that lags slightly behind the wave that drove it. These secondary waves do not scatter away at random, because the atoms are driven in step by the same passing field. Their contributions add together in the forward direction, marching coherently alongside the original. What continues through the glass is the superposition of the incoming wave and all these re-radiated wavelets. And that combined wave has its crests, shifted slightly back at every layer of atoms. Crest by crest, the pattern advances more slowly than the wave would in empty space. Nothing here is destroyed or recreated. The energy moves forward continuously. What we call the slowing of light in a medium is this steady accumulation of phase delay, and it explains something the simple model cannot: why different colors slow by different amounts, why a prism splits white light into its spectrum, why a rainbow exists at all. Once light is understood as a wave being continuously reshaped by everything it passes through, the tidy notion of a straight line becomes harder to defend. Consider what happens when light bends as it crosses from air into water, the phenomenon called refraction that lets a straw appear broken in a glass. The schoolbook gives a rule for the angle and leaves it there, but the deeper question is why light should bend at all. And the answer was first glimpsed in the 17th century by Pierre de Fermat, who proposed something that sounds almost teleological. Light, Fermat suggested, travels between 2 points along the path that takes the least time, not the shortest path, the fastest one. When the 2 points lie in different media where light moves at different speeds, the quickest route is not a straight line, but a bent one, angling so as to spend less distance in the slower material, exactly as a lifeguard running to a drowning swimmer should cover more ground on the sand where running is fast and less in the water where progress is slow. The bending of light at the surface of the water is light obeying this principle of least time, but the principle carries an implication that troubled thinkers for centuries. How does a beam of light, at the instant it leaves its source, behave as though it already knew which path would turn out to be the fastest? The answer, when it finally came, did not restore the straight line. It reframed it entirely. In the middle of the 20th century, the physicist Richard Feynman developed a description of light, building on the quantum theory then taking shape, that remains difficult to absorb even for those who use it daily. Light, in this account, should not be thought of as taking a single path from source to destination. To predict where it will go, one must consider every possible path between those 2 points: the direct line, the shallow detour, the route that loops absurdly out and back. Each conceivable path contributes to the final result, carrying a phase that can be pictured as a tiny rotating arrow. And when the arrows from all these paths are added together, the great majority cancel one another out. The wild detours point in random directions and sum to nothing. Only the paths clustered tightly around the route of least time point in nearly the same direction and survive, reinforcing one another into the bright, apparently straight beam we observe. The straight line, in this framework, is not a track that light follows, but what remains after all the alternatives have interfered away. Light appears to travel in a line for much the same reason a crowd can appear to hold a single opinion. The dissenting voices cancel, and only the consensus is heard. This is more than a mathematical convenience, and the influence of those normally hidden paths can be demonstrated. Take a beam of light and place in its way a diffraction grating, a surface scored with fine parallel lines, and the light will emerge directed into angles that a single straight path could never produce. The grating works precisely by blocking some of the contributions that would otherwise have canceled, unmasking paths that are normally suppressed, and allowing light to be seen going where simple geometry says it should not. The same logic governs the lens in a camera and the mirror in a telescope. Each is a device for managing the interference of innumerable paths, for arranging which contributions reinforce and which cancel. Every sharp photograph ever taken is a record of light behaving in a way the yellow arrow cannot capture. Even the claim that light moves at a single speed dissolves, under careful examination, into something more subtle than the famous number suggests. Physicists distinguish between the phase velocity of a wave and its group velocity, between the speed of the individual ripples and the speed of the packet they form, and in certain carefully engineered materials, these two can diverge dramatically. In some media, the group velocity of a light pulse can be slowed to a crawl. In a celebrated set of experiments at the end of the 20th century, researchers used a cloud of ultra-cold sodium atoms to slow a pulse of light to about 17 meters per second, slower than a bicycle. Later refinements brought a pulse to a halt, storing its imprint in the atoms themselves, and then releasing it to continue on its way, as though light had been set down for a moment and picked back up. None of this breaks the cosmic speed limit, because no information or energy outruns c, but it makes the idea of a single fixed speed for light far too simple. The speed at which a pulse of light arrives depends on what it is traveling through. And then there is a subtler matter still, one rarely raised outside specialist discussions. We speak confidently of the speed of light, but every measurement ever made of that speed has, on close inspection, involved light making a round trip, traveling out to a distant mirror and returning, with the total distance divided by the total time. This yields the average speed over the journey out and the journey back. It does not, by itself, establish that light travels at exactly the same speed in each direction. To measure the one-way speed, you would need a clock at each end of the path, and the two clocks would have to be synchronized. Yet any method of synchronizing distant clocks already presupposes how fast some signal travels between them. Einstein addressed this directly when he built special relativity. Rather than claiming to have proven that light's one-way speed is identical in every direction, he chose to define it that way, adopting equal speeds in all directions as the simplest and most symmetric convention on which to base the synchronization of clocks. Physicists since have examined whether this is merely convenient or genuinely the only possibility, and the careful conclusion is that a range of alternative conventions in which light is faster in one direction and correspondingly slower in the other can be made consistent with experiment. Provided the round-trip average always comes out to c, the theory's physical predictions do not depend on which convention you choose. What this means is modest but real. The isotropy of light's one-way speed is, at least in part, a choice we make to keep the description simple rather than a fact independently read off from nature. The most famous speed in physics rests, in one direction, on an agreement. Step back from the laboratory and look at the sky, and light's refusal to travel as taught becomes a property of the universe at its largest scale. Light does not move in straight lines across the cosmos, because the cosmos itself is not flat. Mass curves the geometry of space and time, and light, following the straightest available path through a curved geometry, traces a curve. Starlight passing near the Sunday is deflected, a prediction confirmed during the solar eclipse of 1919, when stars near the darkened Sunday appeared shifted from their true positions, the observation that made Einstein famous almost overnight. On grander scales, entire galaxies bend the light of more distant galaxies behind them, smearing them into arcs and rings, sometimes producing several images of a single object, so that astronomers can see the same distant source in more than one place at once, its light having taken different curved routes around an intervening mass and arrived along separate paths. The straight yellow line on the chalkboard does not survive contact with gravity. Across the universe, light follows the shape of space, and the shape of space is rarely straight. There is one final reversal, the quietest and perhaps the most profound. Because light takes time to travel, and because that time can be vast, to look out into space is to look backward into time. And we never see distant things as they are, only as they were when their light departed. The Sunday you see is the Sunday of about 8 minutes ago. The night sky is a composite of moments scattered across thousands of years. Some of its light coming from objects that have since changed beyond recognition, their earlier image, still in transit toward us. The most distant light we can detect, the faint background glow that fills the entire sky, set out roughly 14 billion years ago, when the universe first cooled enough to become transparent. And it is reaching our instruments only now, a signal from a cosmos that no longer resembles the one that released it. Light does not simply cross space. It carries the past into the present, and in doing so, it makes every act of seeing, in some small measure, an act of looking back. So the simple lesson, the yellow arrow on the board, was never quite a lie. It was a mercy, a first approximation gentle enough for a child. But the truth it conceals is the better story. Light does not follow a single line. Its straightness is what survives after countless alternative paths cancel. It does not have one fixed speed. It carries the speed of whatever it moves through. And even the equality of its speed in opposite directions is partly a convention we adopt rather than a fact we have measured. It does not slow in glass by pushing through resistance, but by the patient accumulation of phase as its own re-radiated waves fall into step behind it. It does not travel straight across the heavens, but follows the curving shape of space itself, and it does not show us the present, only the gathered past. The next time light enters your eye, having crossed a room or a galaxy to reach you, it is worth remembering that almost nothing about its journey resembles the line you were taught to draw. The reality is harder to picture and impossible to sketch, and that difficulty is not a failure of understanding, but the beginning of it.